Eh, Welcome everyone once again to the Agroecology webinar series. I hope you had a great summer. We are just starting over with the crop series in agroecology. My name is Evelyn Zuniga, and I am one of the communications officers for the Agroecology Partnership Project. If you haven't been here before, the Agroecology Partnership officially started in January 2024 and is funded under the Horizon Europe program. And it currently unites the European Commission and 72 partners across 26 member states, associated countries, and third countries. This partnership seeks to support the agriculture sector to meet the targets and challenges from climate change, biodiversity loss, food security and sovereignty, and the environment. The partnership combines the resources from the European Commission and participating countries to fund research that generates essential knowledge and innovative technologies that align with its goals. This is the fourth webinar in the series Agroecology Crops, which started like around June this year. In this series, we are going to we are exploring key practices and innovations that contribute to maintaining healthy and productive crop for resilient ecosystems. Just a housekeeping announcement. Please feel free to type your questions in the Q&A and the chat section that I have enabled for everyone. I'm going to do my best to address as many as possible within the time that we have. Today, we are very fortunate to have two panelists, Dr. Maryam Rahimi Jahangirlou and Magnus Kamau Lindhardt. Just give me 1 second. I need to start sharing my screen. And this one. Yeah. Okay. Yeah, perfect. Okay. Uh, Dr. Jahangirlou is a postdoctoral researcher at the Department of Agroecology in the Climate and Water section at Aarhus University, and Magnus is a PhD student at the same department in Aarhus University as well. Dr. Jahangirlou's research interests center on carbon reduction, climate-smart agriculture, and cropping systems analysis. Her work emphasizes the integration of field observations to promote sustainable land use and precision farming. She has published several peer-reviewed papers in the field of crop science and actively contributes to advancing research at the intersection of innovative production systems, environmental sustainability, and new technologies. And Mr. Lindhardt's research lie in the integration of renewable solar energy with sustainable agricultural systems through agrivoltaics. As part of the Value for Farm project, his work explores how vertical agrivoltaic systems influence microclimate and their downstream effects on crop performance, including resilience to climate extremes, productivity, and quality. His research further examines the implications of plant soil nutrients dynamics and circular use of nutrients and energy, with a focus on optimizing both land use and resource efficiency with multifunctional farming systems. They both are part of the Value for Farm project, which is entitled Sustainable Renewable Energy Value for Chains for Answering Farmers' Needs, and this was funded under the Horizon Europe program. So, Maryam and Magnus, thank you very much for joining us today and for sharing some insights on this project. And I'm just gonna stop sharing my screen, and the floor is all yours. Thank you very much.
Thank you.
Yeah.
Yeah, perfect.
Hi, Evelyn and all
Hi.
the participants. First, thank you, Evelyn, for organizing this webinar and having us here. As you mentioned, I'm Maryam. I'm postdoctoral researcher at Department of Agroecology. And together with my colleague Kamau, we are working on Value for Farm project, these initiatives of testing integrated agrivoltaic systems. And today we want to talk a little bit about Value for Farm project and respond some of the questions of farmers, of the researchers in this field. Yeah, if I can share my screen, I'm gonna show you my slides. Please let me know if you can see it right now or not. Yeah, you can see it?
Yeah,
Yeah,
Yeah.
great. Yeah. Uh, During my 10 minutes talk, I give you some information a little bit about greenhouse gas emissions contributors, and then how agrivoltaics can bring a co-beneficial solutions to respond to some of those climate change impacts, and what is the key fundamentals of successful agrivoltaics to meet farmers' needs, and what we have in value for farm projects beyond agrivoltaics, which is this integrated agrivoltaic systems. And then Kamau, I think, will go through the value for farm details and what is its work packages and protocols and uh, our trials here. And then at the end, we have 10 minutes for question and answers. Yeah. As you may know, today greenhouse gas emissions can be traced back to 5 economic sectors at top: energy, and then agriculture, industrial process waste, and land use change. Right now, the energy sectors contribute to more than 70% of worldwide greenhouse gas emissions. But please consider that this is at global scales. In European countries such as Britain and Denmark, when more than half of the countries is agriculture, the contribution of agriculture in greenhouse gas emissions it's much higher. To respond to this problem, a big solution comes to using renewables instead of fossil fuels, but it is also based on land-based renewables like biomass, biofuels, or large solar or wind farms on cropland. That this can bring uh, energy versus food production conflicts, and we should respond to this one. Uh, yeah. Uh, at EU level, right now, renewables account for more than 40% of gross electricity generation, mainly wind and hydropower. But solar power, while they have a smaller share right now, they are the faster growing source. And there is two challenges by this fast growing. First is that solar panels and agriculture mostly has similar land requirements like abundance of sunlight and relatively flat ground. And also deployment of traditional on-field photovoltaic systems can bring a monotonous landscape and loss of agricultural land. And we should respond to this. One win-win solutions or co-beneficial solutions to respond to these food versus energy conflicts toward decarbonization in both energy and agricultural sections is agrivoltaics. Simply, if we want to define agrivoltaics, it's multifunctional practices of simultaneously using the same land area for both agriculture and solar energy generation. All European Union Green Deal and United Nations already uh, mentioned that solar panels can be a symbol of decentralized power supply and rural development. And this is so important that agrivoltaics can bring solution to respond to these both sectors or greenhouse gas emissions contributors. But how does agrivoltaics can mitigate carbon dioxide equivalent emissions? First is transforming the food energy land use conflicts into a co-beneficial solutions, what I mentioned already, by displacing fossil fuel-based energy with renewable solar power. And it can also enhance soil carbon retention and carbon production via microclimate moderation, because by having a crop in solar parks, you can preserve soil carbon stocks by maintaining active root zones and cover crops, avoid carbon release linked to land degradation or conversion. And this is my own theory that agrivoltaics also can help to carbon farming because it can diversify farmers' income, and bring a financial buffer for them against climate-related crop loss at the year that the yield is lower, they can sell the energy, and this enables them to invest in smart or carbon sequestration practices like cover cropping and no-till farming. And this can be so important. But when it comes to multifunctionality, we should expect that the level of system complexity is also increased. And agrivoltaics, then we can call it APV, in short, represent a complex system situated at the intersection of microclimate, system configuration, crop physiology, and PV technology. And To be effective and have successful agrivoltaic system, we should formulate it to at least respond to one of the region's dominant environmental stresses. It can be drought, it can be heat, it can be excessive sunlight, and it can be also wind, which in our region, the main problem that we want to address is wind. As you see in this picture, right now there is a lot of configuration of solar panels, the traditional one, the fixed tilt one, which you can see at the top of the picture. Right now it can use for crop production, animal husbandry, or ecosystem services. But right now there is this elevated kind of systems that they are using for again, crop production or some configuration for greenhouse solars. And something that right now we are working on is vertical mount agrivoltaic system. Actually, the studies and also our research studies shows that this is a good choice for temperate regions, that there is a lot of wind, because as we have too low sunlight here, it can bring less land shading and less land use as well, because we also here has the problem of limiting land, and also greater protection against wind and produce electricity that can be aligned with consumption patterns. It means in the morning and in the evening, that this one already also addressed in one of our studies, Victoria et al. And about microclimate, the effect of solar panels on microclimate is strongly depends on solar panel configuration. For this configuration that we are working on here, the main effect of solar panels, it's like the traditional shelter screen that always northern country was using it. It's the first on the wind characteristics. It can be wind speed, wind direction, and then temperature, relative humidity, evapotranspiration. And if you are interested more to know how shelter effect can be complex and important, you can go to this publication, Asylums or Court, that they very good, just provided the details of the traditional and modern shelter effects on climate, water balance, and crop yield. And also about crop physiology, you know that the main effect of solar panels is shade, and we should think about it because it can bring a lot of yield loss. But actually, already a meta-analysis by Loeb et al. Showed that most crops can tolerate up to 15% reduction in solar radiation without significant yield loss, where at top berries, fruits, and fruity vegetables may even experience increase in harvestable yield. Then we can also think about it if we want to select crops for cultivate between solar panels. But the problem with this kind of publication is that they only talking about quantity or intensity, not quality of light. And this concerns me because there is still some unaddressed aspects beyond radiation reduction. You know that we we hypothesize that in agrivoltaic system there is some microclimate modulation effect that maybe compensate for radiation reduction. And also right now, this recent advancement in solar cells like selective or spectrum splitting PV instead of these opaque cells, they are right now game changer by improving light quality for the crops, and maybe we should not concern for reduction in light by having those one. That's why I don't think that this kind of studies that only talk about shade by considering the light quantity are so generalizable to agrivoltaics study. But what we wanna show in value for farm is beyond agrivoltaics. Those slides that I showed you was because I intend to say that agrivoltaic system is complex, but in value for farm, we are even one step further than agrivoltaic systems. These integrated agrivoltaic systems that we are testing in value for farm projects, the combination of agrivoltaics with biogas and green biorefinery. This concept was driven by whole system thinking and circular farming to maximize energy between energy and agriculture and advancing decarbonization and sustainability aspects of agri-food systems. And I think my colleague Kamau bring a lot of details about a value for farm and what is our trials here. And if you are interested to know more about our trial, this is our publication. Some of them are accepted and some of them under review, but the preprint is available. Also, we are offering agrivoltaics as part of master program here in Aarhus University. If you are interested, you can take a screenshot from this slide. And this is also the publications I used in my presentation. Kamau, right now, floor is yours, and please continue. And if you want, I can stop sharing or I can continue if you want me to change the slides.
Yeah, it's fine. You can continue. Just you can start by pressing the next.
Yeah.
Yes. So as Maryam was introducing, we have these grand challenges that are interconnected in our rural landscapes. We have, of course, the threats of climate change and the need for adapting and mitigating, as well as biodiversity crises. We need to diversify our rural economies, moving away from these large-scale farmers that are growing monocrops, but having more diversified systems. We need to also increase our focus on energy autonomy and renewable energy integration, and enhance our cropping systems with resilience and resource use efficiency. And ultimately, the land use conflict that Maryam was also highlighting is what ties all these things together. How do we integrate our land use systems so we can provide both food, feed, and energy for our societies? Next one, please. So Value for Farm is a project of a large consortium with 14 partners. You can see the logos here in the illustration below. And the main goal is to develop sustainable agricultural protocols that are compatible with local farmers' practices and also with the renewable energy production within the local context. And to do that, a wide range of renewable energy production systems and storage technologies are being proposed and tested together with the farmers and interacting with local stakeholders, focusing on residue management, electricity production, both on farm but also on a larger scale, as well as heat and mobility needs for farmers, such as tractors, for example. So the idea is to validate the sustainability and circularity of these renewable-based local value chains through demonstrations. And one of these demonstrations is in our university in Denmark, focusing on our pedoclimatic environment. So in order to ensure replicability and widespread use of these demonstration technologies, there's also a number of replication sites in the project where these technologies will then be tested as replication throughout the EU. Next one, please. Yeah, so in our site, now focusing in on Denmark, because as you saw on the map before, we have also Italy and Belgium in part of our consortium, and we are focusing here on the Danish context because that's where we are based. But we have a range of work packages in this large project. And the key one is providing optimized value chains and results and recommendations from each of these local demonstration sites. So these are part of the work package 3. And results from each of these demonstration sites, Denmark, Italy, and Belgium, will then be integrated into the other work packages on assessing and optimizing the value chains. For example, in Germany, they're doing life cycle assessments, and we also have great work on policy recommendations in order to create a comprehensive assessment of these technologies. Here in the pictures, you see our site. It is a site consisting of vertical panels and south-oriented panels. In Value for Farm, we focus mainly on testing the crops under the vertical constellation, and it's based on our experimental farm at Aarhus University. Next one, please. Yeah. So the whole research and experimental setup is kind of using the platform we have available here at AU Viborg at Aarhus University, where we are able to integrate our largest green biorefinery system that we have a demonstration site on campus. We also have the world's largest experimental anaerobic digestion research facility and biomethanation technology, and then as well as our vertical agrivoltaic system. So by integrating these different subsystems, we are able to assess the benefits and the trade-offs in having, let's say, a closed loop system on both nutrient management, but also on energy use. For example, are we able to use some of the electricity produced from the vertical solar panels to drive some of these secondary processes? The green biorefinery uses a lot of energy in pressing and processing the green biomass. In the biomethanation technology, they need energy for injecting hydrogen and maintaining a steady temperature in the reactor. So how can we use these energies in smart ways and provide a variety of different outcomes in both food, feed, and energy as well? So it's really looking at multifunctionality and integration and providing sustainable products across the value chains. Next one, please. Yeah. So in our field site, which is one of these three subsystems, we are developing and demonstrating different types of cropping systems, specifically developed for the pedoclimatic conditions of the North Atlantic region. So this is an area that can be extrapolated into the Netherlands, northern Germany, parts of France and the UK, Netherlands, and so on. And here we are really having a system where we are looking at both empirical data from our on-site climate stations, but also doing some more long-term modeling of what happens on the dynamics of the soil and the cropping system, and then evaluate these effects on the crop and soil as affected by the microclimates of the vertical panels. Because one idea is that they can protect from wind, as Maryam was saying, but how is this related to then the shade that they also cast on the crops? So here in the pictures, you can see below, we have divided our areas between the solar panels into designated plots, which has then been allocated different treatments of fertilization that I will explain in the next slide. Yeah. Yeah. So in our crop rotation, we have 4 years. We have a grass clover followed by a spring barley with an undersown ryegrass. We then harvest the spring barley green in order to increase the green biomass for the biorefinery and also give more chance for the ryegrass to establish itself and provide a good amount of biomass that we can then take 3 cuts maybe later on before we then establish our soybean. The soybean is a quite interesting crop because many people were expecting it to do less well in a cold climate as Denmark, but we actually had pretty good yields. Although we harvested it green as an edamame bean, so we didn't wait until maturity, it was harvested green. And we had fairly good yields, and we then follow after the soybean with a winter wheat that is quite nitrogen demanding, so the nitrogen fixed by the soybean can then be used by the winter wheat. We also have these fertilizer treatments, as I mentioned before. We are trying to adapt so that the fertilizer we give in biogas digestate is comparable with the amount of nitrogen from the mineral fertilizer treatments. So overall, we are resulting in quite some large numbers of digestate, and this is interesting because what we see is that it's possible to have when you have the biogas facility close by, the cost of transportation can be mitigated in this kind of ways. So we are really comparing mineral fertilizer with the biogas digestate. Yeah, next one, please. Yes, so here are some pictures of all the activities that are going on. I think for the sake of time, I will skip this one, but in case you have any questions, for example, to the soybean harvesting and processing and some of the soil analysis we have been doing, as well as the installation of suction cups, you can always reach out to us if you have. But great thanks to all our team here at Aarhus University for the great work. Yeah,
Yeah.
next one. Yes, so for the setup, we have different types of sensors installed. We are measuring, of course, soil water. So how does these panels impact soil evapotranspiration? So we have installed TDR sensors throughout our test facility. And on the scheme below, you see these different plots in orange and purple, and these are the different types of allocations of fertilizer treatments, but also crop residue management, because when we are investigating what are the potential to harvest the straw, for example, and feed it into the biogas plant, we are also assessing what are the negative consequences on that, and are there interactions with the panels. So it's quite a powerful setup, as we are able to look at the interactions between the PV panels and different types of agricultural management practices. So we are monitoring different types of microclimate, radiation, temperature, humidity are some of them. As I mentioned, soil water and the nitrogen leaching is also an important thing. You can see in the images below that where we have these dug these rows. In here we are installing suction cups. I don't know how familiar you all are with this, but it's basically small ceramic cups in a given depth under the soil surface. And these then collect water from the field, and this water can then be sucked out and be analyzed for different compounds. Often nitrate is the most interesting, to look at are there differences in these treatments and are the panels impacting nitrogen leaching, for example. Then we also have assessments on biodiversity that I'm not gonna go into details with. Okay, next one, please. So these are some of the preliminary results we have from our microclimate surveys. And what we see is that if we look, for example, in the graph on the top right corner of wind speed, we can see that between the vertical panels, we do see a large reduction in especially wind from the west. And this is quite the most predominant wind and also the most detrimental wind for crop production in Denmark. And traditionally farmers have placed hedgerows or wooden shelter belts, as Maryam was talking about. But here we are really looking at, can some of these panels also have a similar effect in terms of reducing wind speed? And we do see that. We have more calm winds between the panels. And we have also observed this tunneling effect, where we can see that when the wind comes from, for example, the south, we do get some increased wind speeds coming in because it's being channeled by the panels. So we are looking into some of these dynamics and what effects that might have. The temperature, we don't see a lot of differences, but you also have to keep in mind that very small differences in temperature can have a huge impact on crop development, especially in the early phases of the crop. So are we able to capture some benefits here in the early spring to have a little bit warmer climate? This would be very beneficial. When we are looking at the calculated evapotranspiration, we can see that we indeed have quite a huge reduction in evapotranspiration. Typically, this is evaporation from the soil surface, meaning that there are indications that these panels actually keep the soil moisture for longer and more persistently in the soil, being very interesting in dry conditions. From the soil water measurements we have in the panel on the right below, we can see that depending on the measurement time, we do have higher soil moisture content, especially in the more drier periods of the year between the panels. So this is also something that's quite interesting. We are still following up on this from this year's data collection. Next one, please. Yeah, so some of these challenges we have faced when conducting such a complex experimental setup is that our plots are obviously quite small. So when we are driving with our agricultural machinery, we want to be able to represent farmers' practices as good as possible. But a lot of challenges happen when we are, for example, with a certain driving speed and we have to stop and start the application of liquid digestate. You can see in the image below here, we have some of the digestate flowing into the other plots because we have very squeezedly tight plots, but also because we have a huge amount of digestate in order to be comparable with the mineral fertilizers. So our technicians are really on this, and we have managed to actually significantly reduce these types of errors by adapting the speed and the amounts and also the application split the application into several times of the year. So there's also some challenges on the replication side because we have so many treatments. It has been difficult to capture all the treatments, and then this collaboration with our colleagues at the Institute of Biological and Chemical Engineering. They have that also requires an extra set of coordination. And these EU projects, they often have extremely high goals and expectations, and it's sometimes important to go back to the drawing board and listen to farmers what actually makes sense when we are doing these kind of experimental setups. So this is also a continuous learning process. Okay, next one, please. Yeah, so we just had this paper published recently. And together with other ongoing studies, I would like to share some of our preliminary results. Next one, please. So first of all, this is data from 2023, and we can see that the yields and the impacts of the solar panels really have differences depending on the crop. Here we can see that the red bars, they indicate the yields between the vertical system, and the blue ones between the south-oriented that you saw on the map, and the green is the reference, so outside the solar panels, without any panels. And we can see, for example, for the grain yields of winter wheat, we can see that it's fairly good in the vertical system. We get even a little bit higher than the mean of the reference system between the panels. This is not something that is a trend. It's slightly different this year than it was previously. For the straw, we see also that there is a reasonable yield, but for some reason the yield is lower compared to the reference. Interesting is that the grass clover is one of the crops that are doing particularly well in these partly shaded systems. We see overall that it's doing equally well between the vertical panels, and sometimes even better, as we can see in this year, where we have actually a significant better yield of all the grass clover cuts when it's harvested between the vertical solar panels. So we're also looking into, is this the soil moisture? Is it its ability to withstand the shading? And these kind of things have an effect on this outcome. Next one, please. Yeah, and these are yields from 2024. And as I mentioned before, we have divided our strips between the solar panels into east, middle, and west, because we wanted to kind of get a higher detail of how these yields and the crop quality are impacted in the different cross sections of our PV system. When you're looking at the let's take this plot under the image. You can see that we have grass clover and soybean and winter wheat. And we have then divided each of these yields into a reference. So that's all the yields outside the panels, and then the western strip and the middle and the eastern strip. And what we see is that, for example, for soybean that is more sensitive to the shading, that we see that the crops that receive the morning sun, that is on the western strip, because the sun comes from the east and the shade is then casted on the eastern strip, but the west receive the morning sun. If you kind of can follow me here, we see that the crops that get the morning sun, they have a higher yield or more closer to the reference as compared to the crops that are cultivated in the eastern strips. And this has something to do with the crop physiology. Many crops, they get kind of tired, exhausted of doing photosynthesis, so they prefer actually to have their sunlight in the morning. And this is also why that we see this, especially for the more shade-sensitive crops, and it has been shown also in other studies in literature. The winter wheat, it's slightly different, but we do see the same trend. The western strip is still a bit higher than the one in the east. And we see that the strip in the center, or the middle strip, gets quite close to our reference yield. So this is also very interesting. And when we are talking to farmers, these are some of the concerns that pop up. How is the maturity of crops in this type of system? When to harvest? Can we expect to harvest at the same time, or should we let the crop mature a little bit longer? And depending on the crop and location and these kind of things. So there's a lot of interactions going on here. I think for the sake of time, I'm gonna skip the other plots, but we can just see that there is a significant effect on crop yield, but it also depends on the crop type and the year of production, and also this location within the system. Yeah, that's kind of the summary. Next one. Yes, and then this aspect of fertilization treatments, whether we are fertilizing with biogas digestate or mineral fertilizer, the idea was to apply the similar amount of nitrogen. And we do see here that we get similar yields, at least. So when we are looking at the plot here in the lower left, we see that across the different crops, we do maintain the same yields. This is yields for 2024. And that grass clover has slightly higher yields for the mineral fertilizer application, but we are still looking into whether this is significant or not. But other than that, it's quite good story that we can maintain the same yields for now. And when we are looking at the nitrogen leaching, what is interesting here is that we do have rather similar leaching concentrations. I should note that this is concentrations. We haven't calculated the actual nitrogen leaching in the taking into account the percolation through our system. But we see that between our panels, we have higher leaching, meaning that more nitrogen is being lost from our cropping system compared to outside. So this has something to do with the fact that outside our PV panels, the crops, they grow better. We saw before that there's slightly higher yields outside our PV panels, meaning that the crops can likely take up more nitrogen compared to between the panels where the crops don't grow as well. So more nitrogen is being leached, but we are still looking into how significant this is, and we also need to do some studies on doing, let's say, yield indexed leaching to look at that as well. Next one, please. Yeah, and as Maryam mentioned also in the beginning, we have this looking at the electricity production. We have higher production in the morning and in the evening compared to a traditional solar PV that is south oriented. And this is very interesting because in a country like Denmark, the electricity market is saturated around noon, so that would be like from 11 to 3 p.m. because we have already a high production of wind and solar during those hours. So when developers are looking to establish new solar systems, this effect is also interesting because they can fetch more value for their electricity in these peak hours. So overall, we have a 13% lower production compared to the south-oriented system, but it matches better the demand. Yeah. Next one, please. And we are also looking into this called land equivalent ratio, which is a way of quantifying the additional benefit of integrating the systems compared to having them separately. So if you can imagine a field where we grow wheat on the whole field, and then another scenario where we integrate with the solar panels, then what is the additional benefit of integrating the systems compared to having them separately? And we did this study from yield of 2023. And we see here for each of the different crops, a land equivalent ratio with higher than 1 is good. So it's a little bit confusing, but here you see in the first column of the one that's called ALER percent, that when we have 7.7%, it means that we have 107% more yield compared to the mono system. So for winter wheat, we see that integrating the systems in the vertical, so that's the yellow bars, we see that we actually get almost 18% higher net benefit of integrating the systems. And when we are looking at where does this benefit come from, is it because of the relative crop yield that is increasing, or is it the relative energy yield? We do see that it's because of the crop benefit. So in the vertical systems, we do have a higher crop yield than we have in the south-oriented system. I do understand that this figure is a little bit complex, and we can always get back to it if you have further questions. Next one, please. Yes, so just to briefly mention some of the continued work we are doing is that we are trying to gather all the data we are collecting from the field and then use it in a crop soil model to simulate more long-term effects, because what does these kind of dynamics mean when you are extrapolating into the next 10, 20, 30 years? This is also something farmers are very curious about. How does it impact my soil? How does it impact my long-term crop productivity? So we are trying to answer some of these questions using these kind of models. And we are collaborating with people at KU Leuven in Belgium on simulating, for example, the radiation that is casted between our panels, and then use that as inputs in our model, where we can then model evapotranspiration, nitrogen leaching, as well as setting up different scenarios on studying the effect of wind and temperature as well. So this is some of the ongoing work we are doing. Next one, please. And as part of my PhD project as well, I'm also collaborating with the people at the biogas and the biorefinery subsystems to do a mass flow analysis on these different types of nutrients, resources, and energy, to look at what are the additional benefit or trade-offs of integrating such technologies into a 1,000 hectare Danish farm scenario, and then evaluating some of these trade-offs and synergies in terms of land use. And a 1,000 hectare scenario is not very hypothetical. There are many farms in Denmark that have these sizes or even bigger. So it's also trying to kind of fit our studies and assessment to the Danish context. Yeah. Next one, please. And the way we are doing that is to set up this kind of framework where we are looking at what happened if we extrapolated some of these results from each of the different subsystems, looking at the interactions and the flows of nutrients and energies, and then what would be the outputs of this integrated system, and then potentially compare it to a mono situation where you separate these different technologies. Yeah. And some of these names are also mentioned here in the slide. And if you have further questions to the biorefinery or the biomethylation, we can forward that to our colleagues, or we can try to answer that. Yeah. Next one. Yes. So in the overall value for farm project, we are still demonstrating these optimized value chains. And we have a great collaboration across the whole consortium. For example, the sustainability assessment of these technologies is conducted by UFZ, and we have policy recommendations as well as an open access decision support tool developed by University of Reading and Wageningen University. We are also looking at what are the effects of market uptake on these renewable energy solutions that is being conducted by the EIHP for business models as well for farmers. Yeah, next one, please. Yes, so thank you so much, everyone. I hope I didn't take too much time. You're welcome to reach out to each of us, or we can forward detailed questions to our colleagues if needed. Yeah, thank you.
Okay. Thank you very much, Maryam and Magnus, for this presentation. I have put the website Value for Farm where you can find details of both of them if you have additional questions about the project, and they also have some deliverables already uh, uh, in the website. We have time for maybe one or two questions. So I have one here. So, so Value for Farm, it wants to validate renewable energy value chains across different European contexts, right? So, what factors have you found that are most critical to ensure that the solutions that you're trying to target are replicable across different farm sizes and climates?
Yeah. Uh, Maybe I can answer, and Kamau can bring more details because it's his PhD studies, and definitely knows more details than me. But I think, as I mentioned in my slide, there is a lot of considerations in agrivoltaic system that we should take into account. I think the first one is this microclimate, or the the climate at bigger context, and what is the best uh, for us to consider in terms of a configuration, what configuration of solar panels we should consider, and what crops between those solar panels. And also, with recent PV technologies, if we are living in a country, for example, that there is less radiation, we should think about this recent advancement, as I said, this light selective one. Yeah, as I said, these systems are so complex, and that's why we are still at a testing level of this kind of system to
Mm.
reach to some drafts or map maybe for the future researchers or even farmers to say some recommendation with lower uncertainties. Yeah, it depends to a lot of factors.
Yeah, definitely. Magnus,
Yeah,
do you want to add something?
yeah, because I think also as Mariam, she mentioned that it has something to do with the local context. So when you want to scale up these technologies, then it's important to make them context specific. So, for example, the demonstration site in Italy, they have a completely different type of agrivoltaic installation. It's overhead systems.
Okay.
And this is because in their climate, the main challenge is excessive heat or sunlight. So protecting some of the crops from this detrimental heat can have a huge benefit in terms of crop yield and quality. But in Denmark, we have to really make sure that all the sunlight reaches the crops because of the climate we have, and hope to reduce some of the wind. So it's really going and talking with farmers and talking with people from that area to understand what are the main challenges in order for that. Another challenge is also the grid infrastructure and the local rules and regulations in terms of setting up these type of systems. Each country, sometimes even each municipality, have their own types of regulations. It can be very heavy bureaucracy. So when stakeholders and investment agents want to invest in these type of systems, it can be really a jungle, and it can be difficult to figure out what is allowed where, when, and how. So it
Yeah.
can be a long process. Yeah.
Yeah, exactly. And that was my next question. It was about the grid, like how to kind of solve that problem that in very like remote places the grid is not there, and then the farmers still need
exactly.
infrastructure. So it just
Yeah,
comes to all like bringing
yeah,
more stakeholders into the conversation. So yeah, that's
yeah.
interesting. We have a question here. It says, could agrivoltaics be used as a means for making biological soil decontamination or remediation of heavily degraded soils less expensive or even profitable? Maybe that's
Yeah,
like applied to a different, but
yeah,
could it?
yeah. Maybe I can also answer this one first. Thank you first, Mikhail, for your question. But actually, recently I read a paper about this one. I don't know about very specific kind of contaminants, but I read in that paper that our colleagues did in USA that using agrivoltaics by bringing less stressful condition can somehow improve the biological characteristics of soil. And I know that when we are improving the microbiome condition of the soils, maybe that microbiome or microorganism can also uh, help toward diminishing this kind of problem. But of course, these things that you are mentioning, it's so specific. It really depends on the elements, and I think it is also can be so complex, and it should be tested with designing a specific kind of trials to see which specific elements, which crop, which condition, which configuration. But actually, for me, I also see some kind of very interesting results in agrivoltaic, like this one that I mentioned, that is related to improving the microbiome of the soils between solar panels. Yeah,
All right. I just have this question. It's just very, I'm curious. So I have seen that these solar panels sometimes they move, isn't it? Is there any of the countries
yeah,
uh, doing that type of model where they move kind of with the sun? They're doing.
yeah. In our in Aarhus University, in our other, we have we hold Department of Agroecology, but we have another branch in Flagabia that they are testing this sun tracking and wind tracking systems. That I think these are the next generation of solar panels, the one that we are testing here, and of course they are more developed. But of
Yeah.
course, they are also more expensive, and
Yeah.
they need more infrastructure and also expenses for farmers. They are also testing that one, but of course, as they are sun tracking and also wind tracking, uh, they can be more helpful for the crops for bringing them more
Mhm.
sunlight, maybe. But with vertical, what our hypothesis is that is occupy less land and less shade for the crops at least, but they are more economic.
Yeah, of course. Like it opened a whole kind of worms. Like you need to balance between sustainable for like profitable. Like farmers will need to be able to access this because
Yeah,
there's no. It could
yeah,
be
Mm.
very fantastic, but if it's not, you cannot really buy it. Well, so it's a whole thing.
yeah,
Mm.
Yeah,
yeah,
yeah.
But our partners in University Cattolica in Piacenza in Italy, they are also part of Value for Farm, and they have a dual access tracker system, the overhead system,
Mm.
um, 650 watts, and that is interesting because they are able to adjust both in two axes. So in that way, they're
Oh
able to
wow.
fine tune the amount of shade that is casted on the crops on very local specific areas. So
All
I
right.
know that's something they're going to work on. Also, some different type of tracking algorithms depending on the crop and the season. Can
Mm,
you adjust, for example, the light to the crops
mm.
in the beginning of the season and then reduce it in the end, for example? Yeah,
Yeah. Also incentives from the countries to the farmers will be like a great also for them to be able to access this, as
yeah,
always.
yeah,
Okay, so Mariam and Magnus, thank you very much. I really appreciate having you here. I just noticed that I'm past like many minutes from from the time that we had. I
okay,
think I'm gonna close the webinar here. Thank you everyone for your questions and for attending the webinar. And
yeah.
again, thank you Mariam and Magnus for giving us this insight into this fantastic project.
Yeah, you're welcome. And thank you again, Evelyn, and all the participants for their time. And we
yeah,
are so open for your question. If you have any question, you always can send us an email and we will be happy to be helpful and respond to that.
yeah.
Excellent.
Yeah,
Thank you very much, guys. Thank
yeah,
you. Bye
Thank
bye.
you.
yeah. Bye.
Bye, bye.